100 meters beneath the Swiss mountains lies a machine that some believe could end the world. A 27-kilometer ring where particles smash together at nearly the speed of light. Scientists call it the greatest experiment in history. Conspiracy theorists call it a portal to hell. Millions believe it has already shifted our reality into an alternate timeline. So what is CERN actually doing down there? And why does a statue of Shiva the Destroyer stand at its entrance? But before we begin, do not forget to subscribe, and if you truly enjoy these videos, please leave a like. Let us begin. 100 meters beneath the Swiss countryside lies a machine that some believe could end the world. A circular tunnel stretching 27 kilometers through rock and earth. Inside this ring, particles smaller than atoms race at nearly the speed of light before smashing into each other with energies that recreate the conditions of the universe just moments after the Big Bang. Scientists call it the Large Hadron Collider. Conspiracy theorists call it a portal to hell. The truth, as always, lies somewhere in between, but it is far stranger than either side could imagine. Over the next 2 hours, we will journey through one of the most ambitious scientific endeavors in human history. We will explore the genuine discoveries that have reshaped our understanding of reality. We will confront the wild theories that have spread across the internet like wildfire. And we will ask the questions that keep physicists awake at night. What is dark matter? Why does anything have mass at all? And what happens when you push the boundaries of human knowledge so far that even the scientists themselves cannot predict what they might find? But first, we need to understand how this place came to exist at all. Because the story of CERN is not just a story about science, it is a story about a continent rising from the ashes of the most destructive war in human history and daring to dream of something greater. Chapter 1. The Birth of a Dream. The year is 1945. Europe lies in ruins. Cities that once stood for centuries have been reduced to rubble. Entire generations of young men are gone. The scientific community that had made Europe the centre of human knowledge has been scattered to the winds. Many of the greatest minds fled to America during the war, escaping persecution and contributing to projects like the Manhattan Project. The atomic bomb that ended the war in the Pacific was built largely by European refugees working on American soil. For those scientists who remained in Europe, the situation was bleak. Laboratories had been destroyed, funding was non-existent, and perhaps most devastating of all, the collaborative networks that had allowed physics to flourish in the early 20th century had been shattered by borders, nationalism, and distrust. But even in the darkest moments, a handful of visionary scientists began to imagine something new. What if Europe could rebuild not just its cities, but its scientific ambition? What if the nations that had just finished trying to destroy each other could instead work together on a project so large that no single country could accomplish it alone? The idea seems almost naive when you consider the context. Germany had occupied France for 4 years. Britain had been bombed relentlessly. The wounds were fresh and deep, and yet a small group of physicists began whispering about a European laboratory that would unite the continent through science. One of the first to articulate this vision was a French physicist named Louis de Broglie. In December of 1949, de Broglie stood before the European Cultural Conference in Lausanne and proposed something radical. Europe needed a central laboratory for atomic physics, a place where scientists from different nations could work side by side, pooling their resources and their knowledge. The proposal gained traction, quickly. In June of 1950, the American physicist Isidore Rabi appeared at the 5th UNESCO General Conference in Florence. Rabi was a Nobel laureate and carried enormous prestige. He tabled a resolution calling for UNESCO to assist and encourage the formation of regional research laboratories to increase international scientific collaboration. What Rabi understood, perhaps better than anyone, was that science in the post-war world had changed fundamentally. The great discoveries of the future would require machines so large and so expensive that they were beyond the reach of any single nation. Particle accelerators, the machines that smash atoms together to reveal their inner secrets, were growing larger with each passing year. If European physics was going to compete with the rapidly advancing American program, it would need to combine forces. Within 2 years, things moved with remarkable speed. In 1952, at a UNESCO meeting in Paris, 11 European countries agreed to establish a provisional council for nuclear research. The French name for this body was Conseil européen pour la recherche nucléaire. the acronym spelled CERN. The founders chose their location carefully. Geneva was selected as the site for the new laboratory. The choice was strategic in every sense. Switzerland was neutral, having stayed out of the war. It sat at the geographic heart of Western Europe. And perhaps most importantly, the Swiss people voted in a referendum to welcome the new organisation onto their soil. The groundbreaking ceremony took place in 1954. On a patch of farmland near the village of Meyrin, just outside Geneva, the first shovels broke earth for what would become the most important physics laboratory in the world. The original founding members included 12 nations: Belgium, Denmark, France, Germany, Greece, Italy, the Netherlands, Norway, Sweden, Switzerland, the United Kingdom and Yugoslavia. Think about what this represented. Germany, which had invaded and occupied half of these countries just a decade earlier, was now a founding partner. France, which had suffered under German occupation, was working alongside its former enemy. The nations that had torn each other apart were now pooling their resources to explore the fundamental nature of the universe. The early years were humble by today's standards. CERN's first particle accelerator, a 600 megaelectron-volt synchrocyclotron, began operating in 1957. It was a significant achievement at the time, but laughably small compared to what would come later. The machine could fit inside a modest building. Its maximum energy was a tiny fraction of what modern accelerators achieve. But the synchrocyclotron proved something important. European scientists could work together. The collaborative model functioned, and with each successful experiment, the appetite for bigger and more powerful machines grew. In 1959, CERN commissioned the proton synchrotron. This machine had a circumference of 600 meters and could accelerate protons to energies of 28 billion electron volts. It was a leap forward in capability and ambition. Scientists from across Europe gathered in Geneva to witness collisions that had never been achieved before. The pattern was established: build a machine, push it to its limits, learn everything possible, then build something bigger. This cycle would repeat for decades, each new accelerator dwarfing its predecessor. By the 1970s, CERN had grown from a modest facility into a sprawling campus that straddled the French and Swiss border. Thousands of scientists, engineers and support staff worked on experiments probing the fundamental structure of matter. The organisation had developed a unique culture, one that prized international collaboration above all else. This culture was enshrined in CERN's founding charter. Article 2 states that the organisation shall have no concern with work for military requirements, and the results of its experimental and theoretical work shall be published or otherwise made generally available. In a world still living under the shadow of nuclear weapons, CERN committed itself entirely to peaceful science. Everything discovered at the laboratory would belong to humanity, not to any single nation or military power. The 1980s brought the most ambitious project yet. CERN decided to build the Large Electron-Positron Collider known as LEP. This machine required a tunnel 27 kilometers in circumference, stretching beneath the Swiss and French countryside. The tunnel passed under farms, villages, and the foothills of the Jura Mountains. Boring machines carved through rock and soil for years. LEP began operation in 1989. It collided electrons with their antimatter counterparts, positrons, at energies never before achieved. The experiments conducted at LEP helped confirm the standard model of particle physics, the theoretical framework that describes all known fundamental particles and their interactions. But even as LEP was producing groundbreaking results, the scientists at CERN were already dreaming of something bigger. The electron-positron collisions were precise but limited in the energies they could reach. To probe deeper into the mysteries of matter, physicists wanted to collide heavier particles at much higher energies. The plan that emerged was audacious. CERN would shut down LEP and use the same tunnel to house an entirely new machine. This machine would collide protons instead of electrons. It would reach energies 7 times higher than any previous accelerator. And it would require technologies that did not yet exist. They called it the Large Hadron Collider. The name comes from 3 parts. Large, because the machine would be the biggest scientific instrument ever constructed. Hadron, because it would collide hadrons, the family of particles that includes protons. And Collider, because unlike some accelerators that fire particles at stationary targets, this machine would smash 2 beams of particles travelling in opposite directions. Planning began in the early 1980s. Construction started in 1998. The project would take over a decade to complete and cost more than €6 billion. Thousands of scientists and engineers from over 100 countries contributed to the design and construction. The technical challenges were staggering. The LHC uses superconducting magnets to bend the paths of protons racing around the ring. These magnets must be cooled to temperatures colder than outer space, just 1.9 degrees above absolute zero. The machine contains more than 90 tons of superfluid helium for cooling. A single sector losing its superconducting state could cause a catastrophic failure. And in fact, this is exactly what happened. On September 10th of 2008, the LHC came to life for the first time. Protons circulated in the tunnel. Scientists around the world celebrated. 9 days later, a faulty electrical connection between two magnets caused a massive helium leak. The resulting damage took over a year to repair and delayed physics operations until November of 2009. But the setback only strengthened resolve. When the LHC finally began collecting data in earnest, it exceeded all expectations. The machine could accelerate protons to 99.999991% of the speed of light. At that velocity, a proton completes 11,000 laps around the 27-kilometer ring every second. The collisions produce temperatures more than 100,000 times hotter than the core of the Sun. From those collisions emerged discoveries that would reshape our understanding of the universe. The most famous came on July 4th of 2012, after decades of searching, after billions of dollars spent, after the combined efforts of thousands of the world's brightest minds. CERN announced that they had found the Higgs boson. The discovery made headlines around the globe. It confirmed a theory proposed nearly 50 years earlier. It explained why particles have mass at all. And it earned the Nobel Prize for the physicists who'd predicted the particle's existence way back in 1964. But the discovery of the Higgs boson was just the beginning. The LHC continues to operate today, producing record amounts of data. Scientists are searching for dark matter, the invisible substance that makes up most of the matter in the universe. They are probing the asymmetry between matter and antimatter that allowed our universe to exist at all. They are looking for evidence of extra dimensions, supersymmetric particles, and phenomena that no theory has yet predicted. And in doing so, they have attracted attention of another kind. Because when you build the largest machine in human history, when you recreate the conditions of the Big Bang, when you search for particles called the God particle, people notice, and some of them begin to wonder, what are they really doing down there beneath those mountains? What doors might they accidentally open? And what might come through? The conspiracy theories surrounding CERN have grown as rapidly as the scientific discoveries. Millions of people believe the laboratory is attempting to open portals to other dimensions. Videos claiming CERN has shifted our timeline into an alternate reality have been viewed billions of times. Religious groups have accused the scientists of trying to summon demons or destroy the universe itself. CERN has responded to these theories directly, posting explanations on their website, producing videos debunking the most popular claims. But the theories persist and multiply. Every new experiment provides fresh fuel for speculation. Every unusual observation spawns 1,000 explanations stranger than the truth. What is remarkable is that the actual science being done at CERN is in many ways stranger than the conspiracy theories. Particles that exist for fractions of a second before decaying into showers of other particles, antimatter that annihilates on contact with ordinary matter, fields that permeate all of space and give mass to everything that exists, quantum effects where particles seem to be in two places at once until observed. The universe revealed by particle physics is bizarre beyond imagination. It operates according to rules that violate common sense at every turn, and the scientists at CERN spend their careers trying to make sense of it all, piece by piece, collision by collision. From the ashes of World War II, Europe built a monument to human curiosity, a place where former enemies work side by side, a machine that recreates the first moments of creation, a community dedicated to understanding the deepest secrets of existence. The dream that began in 1949 with a handful of visionaries has become the largest scientific collaboration in history. Today, CERN has 25 member states. Scientists from over 100 countries participate in experiments. The laboratory employs roughly 3,000 people and hosts more than 17,000 visiting researchers each year. They are still building. They are still dreaming. and what they find next may change everything we thought we knew about reality itself. But to understand what they are searching for, we first need to understand how the machine actually works. In the next chapter, we will descend into the tunnel itself and follow a proton on its journey through the most complex scientific instrument ever constructed. Chapter 2. The Machine Beneath the Mountains. 100 meters below the rolling farmland of the Swiss and French countryside, a tunnel stretches in a perfect circle for 27 kilometers. If you could drive through it, the journey would take about 20 minutes. But nothing human ever travels through this tunnel, only particles smaller than atoms racing at nearly the speed of light, completing 11,000 laps every single second. The Large Hadron Collider is not just a machine. It is thousands of machines working in perfect harmony. It is a symphony of engineering so complex that describing it requires a new vocabulary. And yet at its core, the principle is beautifully simple. Take particles, speed them up, smash them together, see what comes out. Let us follow a proton on its journey through the LHC. Our proton begins its life inside a bottle of hydrogen gas. Hydrogen is the simplest element in the universe, consisting of a single proton orbited by a single electron. When scientists want to feed the LHC, they extract protons from hydrogen by stripping away the electrons. The first stage of acceleration happens in a device called LINAC 4. This linear accelerator uses electric fields that oscillate at precisely timed intervals to push the protons forward. By the time our proton exits LINAC 4, it has reached about 1/3 of the speed of light. This might seem impressive, but it is just the beginning. From LINAC 4, the proton enters the proton synchrotron booster. This is a circular accelerator about 157 meters in circumference. Here the proton joins billions of others, all traveling together in bunches. The synchrotron uses magnets to bend the protons into a circular path, while radio frequency cavities push them to higher and higher speeds. But the booster is still just a warm-up. Next comes the proton synchrotron itself, the machine that dates back to 1959. Despite being over 65 years old, it remains a crucial part of the accelerator chain. The PS takes our proton and accelerates it further, increasing its energy by a factor of 25. Then comes the superproton synchrotron, or SPF. This machine has a circumference of nearly 7 kilometers. It was once the flagship accelerator at CERN, used for Nobel Prize-winning discoveries in the 1980s. Now it serves as the final step before the LHC itself. By the time our proton leaves the SPS, it has reached energies of 450 billion electron volts. Finally, our proton enters the Large Hadron Collider. The LHC tunnel lies 100 meters underground at its deepest point and about 50 meters at its shallowest. The tunnel was originally built for the Large Electron-Positron Collider in the 1980s. When LEP was decommissioned, the LHC inherited its home. Inside the tunnel, our proton finds itself in one of two parallel beam pipes, each about 3 centimeters in diameter. These pipes are kept at an almost perfect vacuum, one of the emptiest spaces on Earth. At atmospheric pressure, air molecules would scatter the protons and ruin the beam within seconds, so engineers pump out the gas until fewer molecules remain per cubic centimeter than exist in interplanetary space. Surrounding the beam pipes are the superconducting magnets. These are the heart of the LHC. To bend protons traveling at nearly the speed of light around a 27-kilometer ring requires magnetic fields of tremendous strength. The LHC uses magnets that produce fields of over 8 Tesla, roughly 160,000 times stronger than Earth's magnetic field. Creating such powerful magnetic fields with conventional electromagnets would require impossibly large amounts of electricity. The magnets would also generate so much heat that they would melt. So the LHC uses superconductors instead. Superconductivity is one of the strangest phenomena in physics. When certain materials are cooled to extremely low temperatures, their electrical resistance drops to exactly zero. Current can flow through them forever without losing any energy. The LHC magnets use coils made from niobium titanium alloy, cooled by superfluid helium to just 1.9 degrees above absolute zero. This is colder than the average temperature of outer space. There are 1,232 main dipole magnets arranged around the ring. Each one weighs about 35 tons and is nearly 15 meters long. These dipoles bend the proton beam into its circular path. Another 392 quadrupole magnets focus the beam, squeezing the bunches of protons tighter together. As our proton races around the ring, It passes through radio frequency cavities that give it a push on each lap. Think of pushing a child on a swing. Each push must come at exactly the right moment to add energy to the motion. The RF cavities operate at frequencies of 400 million cycles per second, perfectly synchronized with the bunches of protons. Over the course of about 20 minutes, the LHC ramps up the energy of the proton beams. Starting from the 450 billion electron volts delivered by the SPS, the machine pushes the protons to 6.5 trillion electron volts. At this energy, each proton carries as much energy as a flying mosquito. That might not sound like much, but remember that a proton is about a trillion times lighter than a mosquito. The energy density is astronomical. Now comes the crucial part. The LHC is a collider, which means it needs two beams travelling in opposite directions. While our proton has been racing clockwise around the ring, another beam has been travelling counterclockwise. The two beams pass through separate beam pipes for most of the journey, but at 4 points around the ring, the pipes merge and the beams cross. These crossing points are where the real action happens. Here, giant detectors surround the collision region, waiting to catch every particle that emerges from the impacts. The four main detectors are called Atlas, CMS, Alice, and LHCb. Each is a marvel of engineering in its own right. Atlas stands for a toroidal LHC apparatus. It is the largest particle detector ever built, measuring 46 meters long, 25 meters in diameter, and weighing 7,000 tons. If you could hollow it out, you could fit an 8-story building inside. Atlas is a general-purpose detector designed to search for new particles across a wide range of possibilities. CMS stands for Compact Muon Solenoid. Despite the word compact in its name, CMS weighs 14,000 tons and contains more iron than the Eiffel Tower. It earned the compact designation because it is denser than Atlas, packing more detector elements into a smaller space. CMS and Atlas are deliberately designed with different technologies so they can independently confirm each other's discoveries. Alice is optimized for a special type of collision. For part of each year, the LHC switches from colliding protons to colliding lead ions. These heavy ion collisions create conditions similar to those that existed microseconds after the Big Bang, when the universe was a hot soup of quarks and gluons. Alice studies this primordial state of matter. LHCb focuses on a specific type of particle called the beauty quark. By studying how beauty quarks behave, physicists hope to understand why our universe contains matter at all. According to the equations, equal amounts of matter and antimatter should have been created in the Big Bang. They should have annihilated each other, leaving nothing behind. Something broke the symmetry. LHCb is trying to find out what. When two protons collide at the center of these detectors, they do not simply bounce off each other like billiard balls. The collision energy is so high that it creates entirely new particles out of pure energy, following Einstein's famous equation relating energy and mass. The heavier the particle you want to create, the more collision energy you need. This is why physicists keep building bigger accelerators. A typical proton-proton collision at the LHC produces hundreds of particles flying out in all directions. These particles stream through layer after layer of detector systems. First comes the inner tracker, made from millions of silicon sensors that record the paths of charged particles with micrometer precision. Next comes the calorimeters, which measure the energies of particles by absorbing them completely. Finally come the muon systems, which catch the penetrating particles called muons that pass through everything else. The detectors generate enormous amounts of data. At full operation, the LHC produces about 600 million collisions per second. Recording every detail of every collision would require writing 1 petabyte of data every second. No storage system on Earth could handle this, so the detectors use sophisticated triggering systems to decide which collisions are interesting enough to keep. These triggers examine each collision in real time and make decisions in microseconds. Out of 600 million collisions per second, only about 1,000 are recorded for later analysis. The rest are discarded forever. Even with this filtering, the LHC experiments generate about 50 petabytes of data per year. To analyze this flood of information, CERN created a global network of computing centers called the Worldwide LHC Computing Grid. Over 170 sites in 42 countries contribute processing power. It is one of the largest distributed computing projects in existence. The engineering challenges do not end with the machine itself. The LHC consumes about 120 megawatts of electricity when operating. This is enough to power a small city. The electric bill for a year of operation runs into the tens of millions of euros. Keeping the magnets cold requires constant work. The cryogenic system that maintains the superfluid helium is the largest in the world. About 96 tons of helium circulate through the system. If anything goes wrong, if a single magnet loses its superconductivity in an event called a quench, the stored energy must be safely discharged. The LHC contains enough stored magnetic energy to melt about 15 tons of copper. The accelerator also presents unique radiation challenges. When protons collide, some of the resulting particles escape the detectors and embed themselves in the surrounding rock. Over years of operation, certain areas around the tunnel have become radioactive enough to require careful management. Workers who enter the tunnel during maintenance periods must follow strict safety protocols. Despite all these challenges, the LHC operates with remarkable reliability. During a typical year, the machine delivers beams for physics for about 300 days. The rest of the time is dedicated to maintenance, upgrades, and technical stops. Each improvement in performance translates directly into scientific discovery. The key metric is something called integrated luminosity, a measure of how many collisions have been delivered to the experiments. Higher luminosity means more collisions, which means more chances to observe rare processes. In 2025, the LHC achieved new records. For the first time, it collided oxygen and neon ions, not just protons and lead. These lighter ion collisions provide unique windows into nuclear structure. Studies quickly confirmed something remarkable about neon nuclei. Their shape is not spherical, but elongated, like a bowling pin. The proton physics program also exceeded targets. The machine delivered 125 inverse femtobarns to the ATLAS and CMS experiments, surpassing the previous year's record by a small but significant margin. Each femtobarn represents roughly 80 trillion proton-proton collisions, but the current LHC is not the final word. Already engineers are preparing for the high luminosity upgrade, scheduled for completion in 2030. This upgraded machine will deliver 5 times more collisions per second than the current configuration. New magnets, new focusing systems, and new detector components will enable an entire new generation of discoveries. Beyond the high luminosity LHC lies something even more ambitious. CERN is planning the Future Circular Collider, a machine that would dwarf the current LHC. The proposed tunnel would stretch 91 kilometers in circumference, more than 3 times the size of the LHC. It would reach collision energies of 100 trillion electron volts, 7 times higher than currently possible. The Future Circular Collider would follow the same 2-stage approach that led from LEP to the LHC. First, an electron-positron machine would enable precision measurements of the Higgs boson and other particles. Then a proton-proton collider would push to the highest possible energies, searching for entirely new physics. The estimated cost is 15 billion Swiss francs. Construction could begin in the early 2030s with first operation in the mid-2040s. The machine would likely run until the end of the century, providing employment for generations of physicists and engineers. Not everyone agrees that such a massive investment is warranted. Some argue that the era of ever larger colliders should give way to smaller, more targeted experiments. Others question whether particle physics deserves such a large share of science funding when other fields might produce more immediate benefits. The debate continues within the physics community and beyond. But for now, the LHC remains the frontier. Every day it operates, protons circle the ring 11,000 times per second. They collide with energies that existed naturally only in the first moments after the Big Bang. And from those collisions emerge particles that hold the secrets of the universe. Scientists did not build this machine on a whim. They built it to answer specific questions that had haunted physics for decades. Chief among them was the mystery of mass. Why do particles weigh anything at all? Why do some particles have enormous masses while others weigh nothing? The answer lay in a theoretical mechanism proposed in 1964 and finally confirmed nearly 50 years later. In the next chapter, we will explore the hunt for the Higgs boson, the particle that earned the nickname the God particle and whose discovery marked the greatest triumph in the history of the Large Hadron Collider. Chapter 3. The God particle. There is a question so fundamental that it borders on the absurd. Why does anything have mass at all? When you pick up a rock, why does it resist your push? When you throw a ball, why does it take effort to accelerate it? We take mass for granted in everyday life, but for physicists in the middle of the 20th century, its origin remained a profound mystery. The equations that describe particles and forces are elegant and precise. They predict the outcomes of experiments with remarkable accuracy. But there was a problem. The most beautiful versions of these equations only worked if all particles had zero mass. The mathematics was gorgeous, but clearly wrong. Electrons have mass. Protons have mass. Everything around us has mass. Reality refused to match the theory. In 1964, several groups of physicists independently proposed a solution. In Belgium, Robert Brute and François Englert published a paper suggesting that space itself might be filled with an invisible field. Particles moving through this field would interact with it, and that interaction would give them mass. A few weeks later in Scotland, Peter Higgs published a similar idea and added a crucial prediction. If this field existed, there should be a particle associated with it. The mechanism was counterintuitive but powerful. Imagine walking through an empty room. You can move freely in any direction with no resistance. Now imagine the room is filled with a thick invisible fluid, moving through. The fluid requires effort. The more the fluid interacts with you, the harder it is to move, and the more mass you effectively have. According to this theory, empty space is not empty at all. It is permeated by what we now call the Higgs field. Different particles interact with the Higgs field to different degrees. Photons, the particles of light, do not interact with it at all. They remain massless and always travel at the speed of light. Electrons interact weakly and have small masses. The top quark interacts strongly and is enormously heavy, about 185 times heavier than a proton. The theory was elegant and it solved many problems. But there was no way to test it directly in 1964. The particle associated with the Higgs field, the Higgs boson, was predicted to be heavy. Creating it would require energies far beyond what accelerators of that era could achieve. For decades, the Higgs boson remained theoretical, a mathematical necessity that might or might not exist in the real world. Physicists call particles that have been predicted but not yet observed various names. Some called the Higgs boson the champagne bottle, boson, because the mathematics of the Higgs field resembles the shape of the bottom of a champagne bottle. Others called it the God particle, a nickname that most physicists despise but which stuck in the public imagination. The nickname actually comes from a book published in 1993 by Leon Lederman, a Nobel Prize-winning physicist. Lederman wanted to call it the goddamn particle because it was so frustratingly difficult to find. His publisher made him change the title to the God particle instead. Lederman later regretted the choice, noting that the name was taken out of context and implied something religious that he never intended. Peter Higgs himself disliked the nickname. He worried that it would offend religious people and create unnecessary controversy around what was purely a scientific question. But the name captured public attention in a way that Higgs boson never could. Journalists used it relentlessly. By the time the actual discovery came, everyone outside the physics community knew it as the God particle. The search began in earnest in the 1980s. The Large Electron-Positron Collider at CERN started probing the energy ranges where the Higgs might hide. ELEP found nothing but set important limits. The Higgs boson, if it existed, had to be heavier than about 114 billion electron volts. Across the Atlantic, the American physics community was planning its own assault on the Higgs mystery. The superconducting super collider was designed to be the most powerful accelerator ever built. Its tunnel would stretch 87 kilometers beneath the plains of Texas. It would reach energies of 40 trillion electron volts, dwarfing anything else in existence. Construction began in 1991. Miles of tunnel were bored, billions of dollars were spent. Then in 1993, Congress cancelled the project. Cost overruns, changing political priorities, and the end of the Cold War all contributed to the decision. American particle physics was devastated. The dream of finding the Higgs in America died in a hole in Texas. This left CERN as the only realistic hope. The organization responded by accelerating plans for the Large Hadron Collider. The LHC would not reach quite as high energies as the cancelled American machine, but it would be enough. Simulations suggested that the Higgs boson, if it existed in the expected mass range, would be discoverable. The hunt consumed the particle physics community for nearly 2 decades. Thousands of physicists dedicated their careers to building the machine, constructing the detectors, and developing the analysis techniques needed to find a tiny signal amid overwhelming backgrounds. The challenge was immense. The Higgs boson, once created, lives for an unimaginably short time. It exists for less than a billionth of a trillionth of a second before decaying into other particles. You can never see a Higgs boson directly. You can only infer its existence from the particles it leaves behind. Moreover, the Higgs can decay in many different ways. Sometimes it produces 2 photons. Sometimes it produces pairs of heavier particles like Z bosons or W bosons. Sometimes it produces quarks. Each decay mode has different characteristics and different background processes that can mimic the signal. To discover the Higgs, physicists had to search for statistical excesses in multiple decay channels simultaneously. They had to account for every possible background process that could produce similar signals. They had to understand their detectors with exquisite precision. Any systematic error could create a false signal or hide a real one. The LHC began collecting serious data in 2010. For 2 years, trillions of collisions were recorded and analysed. The experiments developed increasingly sophisticated techniques for separating potential Higgs events from the enormous backgrounds. Machine learning algorithms helped identify patterns that human eyes might miss. Throughout 2011 and early 2012, tantalizing hints began to emerge. Both ATLAS and CMS, the 2 general-purpose detectors, saw small excesses in their data around a mass of 125 billion electron volts. The excesses were too small to claim discovery. In particle physics, you need a statistical significance of at least 5 standard deviations, what physicists call 5 sigma, to claim you have found something new. Anything less could be a random fluctuation. The pressure was intense. Rumours swirled through the community. Preliminary results leaked onto blogs and social media. CERN leadership worked to maintain discipline, ensuring that no claims were made prematurely. The worst possible outcome would be to announce a discovery that later turned out to be a statistical fluke. By mid-2012, both experiments had collected enough data to make definitive statements. CERN scheduled a major seminar for July 4th, inviting scientists from around the world. The auditorium was packed. Dozens of physicists who had worked on the search for decades sat in the front rows. Peter Higgs himself, then 83 years old, was present. The presentations told the story through data. Graph after graph showed small bumps, slight excesses, hints of something new. Separately, each channel was suggestive but not conclusive. Together, the evidence was overwhelming. ATLAS reported a significance of 5.9 sigma. CMS reported 5 sigma. Both experiments saw the same thing at the same mass. The probability that this was a random fluctuation was less than 1 in 3 million. Rolf Hoyer, the CERN Director General at the time, stepped to the microphone. "I think we have it," he said. The auditorium erupted. Scientists wept. Decades of work had culminated in this moment. The Higgs boson was real. Peter Higgs wiped tears from his eyes. He later said it was overwhelming and that he never expected this to happen in his lifetime. Nearly 50 years had passed since he proposed the particle. Most physicists wait their entire careers for experimental validation of their theories. Many never see it. The discovery made headlines around the world. It graced the front pages of newspapers from New York to Tokyo. Television networks broadcast special reports. Politicians offered congratulations. For a brief moment, particle physics captured global attention in a way it rarely does. The Nobel Prize followed quickly. In October 2013, François Englert and Peter Higgs were awarded the Nobel Prize in Physics for the theoretical discovery of a mechanism that contributes to our understanding of the origin of massive subatomic particles. Robert Bratt would have shared the prize, but he had died in 2011, and Nobel Prizes are not awarded posthumously. The discovery confirmed the standard model of particle physics, the theoretical framework that describes all known fundamental particles and forces except gravity. The standard model was developed over several decades, starting in the 1960s. By the time of the Higgs discovery, it had been tested in thousands of experiments and always emerged victorious. But without the Higgs boson, the model had a gaping hole. With the discovery, the picture was complete. Or was it? Even as champagne corks popped and congratulations flowed, physicists knew that finding the Higgs was just the beginning. The Standard Model is remarkably successful but clearly incomplete. It does not explain dark matter, the invisible substance that makes up most of the mass in galaxies. It does not explain why there is more matter than antimatter in the universe. It does not incorporate gravity. It cannot explain why the Higgs boson has the mass it does, rather than some other value. The Higgs boson itself might provide clues to these deeper mysteries. Detailed studies of its properties could reveal subtle deviations from Standard Model predictions. Any such deviation would point toward new physics beyond our current understanding. Since 2012, CERN has been studying the Higgs boson intensively. The experiments have measured its mass with incredible precision, 125.35 billion electron volts, with an uncertainty of less than 1%. They have observed it decaying into multiple different types of particles. They have measured the rates of these decays and compared them to theoretical predictions. So far, everything matches the Standard Model perfectly. The Higgs boson behaves exactly as predicted. This is both a triumph and a disappointment. A triumph because it confirms our theories, a disappointment because physicists were hoping to find cracks in the Standard Model that would point toward new discoveries. The search continues. In 2025, the Atlas experiment announced new results at the European Physical Society conference. They had found evidence, though not yet at discovery level, that the Higgs boson decays into muons. This decay is exceedingly rare, occurring in only about 1 out of every 5,000 Higgs decays. Observing it requires enormous amounts of data and exquisite detector performance. The muon decay channel is special because muons are second-generation fermions. The Higgs mechanism gives mass to all fermions, but until recently, Higgs decays had only been directly observed to heavier third-generation particles like tau leptons and bottom quarks. Seeing the decay to muons confirms that the Higgs field interacts with second-generation particles as expected. Scientists are also searching for rare Higgs decays that could reveal new physics. One particularly interesting channel is the decay of a Higgs boson into a Z boson and a photon. In the Standard Model, this decay is extremely rare and proceeds through a complicated quantum process. Any enhancement of this decay rate would indicate new particles participating in the process. The next major milestone will be measuring the Higgs self-interaction. The Higgs field has a peculiar property. It not only gives mass to other particles, but also gives mass to the Higgs boson itself. This self-interaction should cause pairs of Higgs bosons to occasionally be produced together in collisions. Observing this double Higgs production would confirm a fundamental prediction of the theory. But double Higgs events are extraordinarily rare. The LHC produces only a handful per year with current conditions. Detecting them requires the high luminosity upgrade, which will increase the collision rate by a factor of 5. Even then, it will take years of data collection to accumulate enough events for a statistically significant measurement. Beyond precision studies, physicists are also searching for cousins of the Higgs boson. Some theories predict that the Higgs we discovered is just one member of a larger family. There might be heavier Higgs bosons, charged Higgs bosons, or Higgs bosons with different properties. Finding any of these would revolutionize physics. The hunt for the Higgs boson ended in 2012 with triumphant success. But in another sense, it was just the opening chapter of a longer story. The particle that gives mass to everything in the universe has been found. Now the task is to understand it fully, and to use that understanding to peer even deeper into the nature of reality. The discovery answered one of physics' deepest questions, but it also inspired questions of a very different kind. When CERN announced they were searching for the God particle, some people took the name literally. They saw in the massive machine beneath Geneva something more than science. They saw a challenge to religion, a threat to the natural order, perhaps, even a gateway to something supernatural. Standing at the entrance to the CERN campus is a statue that only deepens these suspicions, a 2-meter bronze figure of the Hindu god Shiva, dancing within a ring of flames. The statue was a gift from India celebrating scientific collaboration, but to many observers, it seemed to confirm their darkest fears about what was really happening underground. In the next chapter, we will explore the strange symbolism of CERN and how a statue meant to celebrate international cooperation became the centerpiece of conspiracy theories that span the globe. Chapter 4: The Dance of Creation and Destruction. On June 18th of 2004, a ceremony took place at CERN that would fuel conspiracy theories for decades. A 2-meter-tall bronze statue was unveiled in a courtyard outside one of the laboratory buildings. The statue depicted a figure with 4 arms, dancing within a ring of fire. In one hand, the figure held a drum, in another, flame. One hand was raised in a gesture of blessing. One foot trampled a small demon. The figure was Shiva, one of the principal deities of Hinduism. Specifically, it was Shiva in his aspect as Nataraja, the Lord of Dance. The statue was a gift from the government of India to celebrate decades of scientific collaboration between Indian researchers and CERN. To the scientist at CERN, the statue was a meaningful symbol of an ancient philosophical idea finding resonance in modern physics. To conspiracy theorists around the world, it was proof that something sinister was happening beneath the mountains of Switzerland. Understanding why India gave this particular gift requires understanding what Nataraja represents in Hindu cosmology. Shiva is not simply a destroyer, despite that being his most common description in Western sources. In the Hindu triumvirate of Brahma, the creator, Vishnu the preserver, and Shiva the destroyer, Shiva plays a more nuanced role. Destruction in this context is not evil. It is part of an eternal cycle. Old things must be destroyed to make way for new things. Death enables rebirth. Endings enable beginnings. The dance of Nataraja represents this cosmic cycle. The drum in his right hand symbolizes creation, the first sound from which the universe emerged. The flame in his left hand symbolizes destruction, the fire that will consume the universe at the end of time. His raised hand offers protection and blessing to his devotees. His other hand points to his lifted foot, symbolizing liberation from the cycle of rebirth. The demon beneath his other foot represents ignorance, the darkness that prevents enlightenment. The ring of fire surrounding the dancing figure represents the cosmos itself, the endless cycle of time. Shiva dances within this cycle, driving it forward, embodying both the creative and destructive forces that shape all of existence. When Indian officials chose this image as their gift to CERN, they saw a profound connection to particle physics. At CERN, scientists study the fundamental building blocks of the universe. They recreate the conditions of the Big Bang, the moment of ultimate creation. They observe particles winking into existence and annihilating back into energy, a microscopic dance of creation and destruction, happening billions of times every second. The renowned physicist Fritjof Capra had drawn this connection decades earlier. In his 1975 book, The Tao of Physics, Capra compared the dance of Nataraja to the behavior of subatomic particles. He wrote that modern physics has shown that the rhythm of creation and destruction is not only manifest in the turn of the seasons and in the birth and death of all living creatures, but is also the very essence of inorganic matter. A plaque next to the statue at CERN quotes Capra. Hundreds of years ago, Indian artists created visual images of dancing Shivas in a beautiful series of bronzes. In our time, physicists have used the most advanced technology to portray the patterns of the cosmic dance. The metaphor of the cosmic dance thus unifies ancient mythology, religious art, and modern physics. For the scientists at CERN, this was a beautiful synthesis of ideas from different cultures, finding common ground in the pursuit of understanding. For those already suspicious of what CERN was doing, it looked like something else entirely. The conspiracy theories had been brewing for years before the statue arrived. The scale and cost of the Large Hadron Collider naturally attracted attention. The exotic terminology of particle physics, with its talk of God particles and dark matter and antimatter, sounded almost mystical to those unfamiliar with the science. When the statue was unveiled, conspiracy theorists seized upon it as confirmation of their fears. Why would a scientific laboratory erect a statue of a deity associated with destruction? What did this say about CERN's true intentions? Were the scientists not content to merely study the universe but actually seeking to destroy it? The theories multiplied and evolved. Some claimed that CERN was attempting to open a portal to another dimension. The circular shape of the Large Hadron Collider was likened to a stargate, a doorway through which something might emerge. The extreme energies of the collisions were described as tearing holes in the fabric of reality. Others went further, claiming that CERN was attempting to summon demonic entities. The statue of Shiva was reinterpreted not as a metaphor for the cosmic cycle, but as a literal invitation to dark forces. The Ring of Fire became a portal to hell. The scientists became cultists performing arcane rituals beneath the earth. Still others focused on the CERN logo itself. The stylized letters that spell CERN were said to contain hidden sixes, forming the number of the beast. This claim requires considerable imagination, as the logo is simply a representation of particle tracks from early accelerator experiments. But to those determined to find hidden meanings, the connection seemed obvious. The theories were amplified by genuine scientific concepts that sounded alarming when stripped of context. CERN scientists do talk about creating microscopic black holes. They do study antimatter. They do recreate conditions from the early universe. Each of these facts, presented without explanation, sounds like the beginning of a science fiction disaster movie. CERN has repeatedly addressed these concerns directly. Their website includes a frequently asked questions section that tackles the most common conspiracy claims. On the question of black holes, they explain that any microscopic black holes created in the LHC would be so tiny that they would evaporate almost instantaneously through a process called Hawking radiation. They would pose no threat whatsoever. On the question of the Shiva statue, CERN explains that it was a gift celebrating international collaboration and that Shiva is a symbol of Shakti, or life force, not simply destruction. They note that the cosmic dance of the Nataraja is a metaphor for the modern study of the cosmic dance of subatomic particles. On the question of portals to other dimensions, CERN scientists have been blunt. The energies reached by the LHC, while high by human standards, are routinely exceeded in nature. Cosmic rays from distant stars strike Earth every day with energies far beyond what the LHC can achieve. If such collisions could open portals or destroy the universe, it would have happened long ago. But the explanations have done little to quell the theories. In fact, the very act of CERN responding to the claims has been interpreted by some as evidence that they have something to hide. When an organization feels compelled to deny something, the reasoning goes, perhaps there is truth to the accusation. The statue continues to draw attention. Tourists visiting CERN often ask to see it. Photographs of the Nataraji circulate endlessly on social media, usually accompanied by ominous captions. Every time CERN announces a new experiment or achieves a new milestone, the statue appears in conspiracy videos as proof of malevolent intent. What is striking about the phenomenon is the gap between the intentions of those who gave and received the gift, and those who now interpret it. The Indian government saw Nataraja as a symbol of their ancient philosophical traditions finding validation in modern science. The scientists at CERN saw it as a celebration of international collaboration and a poetic metaphor for their work. The conspiracy theorists see it as a confession of cosmic crimes. This gap reflects something deeper about how science is perceived in the modern world. For many people, particle physics exists in a realm of mystery that is indistinguishable from magic. The terminology is opaque. The scales involved, both the subatomic particles being studied and the massive machines used to study them, are beyond everyday comprehension. The goals, understanding the fundamental nature of reality, sound almost religious. Into this space of mystery, conspiracy theories rush to fill the void. When people cannot understand what scientists are actually doing, they imagine what scientists might be doing. And in that imagination, the strangest possibilities seem plausible. The irony is that the actual science being done at CERN is, in many ways, stranger than the conspiracy theories. Real particle physics involves phenomena that violate common sense at every turn. Particles can be in two places at once until observed. Empty space seethes with virtual particles popping in and out of existence. Time slows down for objects approaching the speed of light. The universe may contain extra dimensions curled up too small to detect. These concepts, all supported by rigorous experimental evidence, sound like science fiction. They require years of study to understand properly. They challenge intuitions developed over millennia of human evolution for navigating a world of middle-sized objects at walking speeds. Perhaps it is inevitable that an institution probing such mysteries would attract suspicion. Perhaps the very strangeness of quantum physics makes any claim about CERN seem believable to those not steeped in the technical details. Perhaps humans are simply pattern-seeking creatures who will find meaning and threat wherever we look. What is certain is that the conspiracy theories show no signs of fading. If anything, they have intensified with the rise of social media. Platforms that reward engagement over accuracy have amplified the most sensational claims. Videos alleging that CERN is opening portals or shifting timelines routinely accumulate millions of views. Debunking videos, while they exist, rarely achieve the same reach. The scientists at CERN have mostly adopted a patient educational approach. They answer questions, they conduct tours, they post explanations online. They invite journalists and content creators to visit and see for themselves. They emphasize that their work is published openly, available for anyone to scrutinize, but they also maintain a sense of humor. When Run 3 of the LHC began in July of 2022, coinciding with the 10th anniversary of the Higgs discovery, social media was flooded with posts claiming CERN was about to open a portal. Scientists at the laboratory responded with jokes and memes. One official CERN tweet showed a live stream of the control room with the caption, "In case you're wondering if we had safely started to collide," with a full shot of the control room. No portals yet. The statue of Nataraja still stands in its courtyard at CERN. It has become one of the most photographed objects on the campus. Scientists pass it on their way to work, perhaps sparing it a glance, perhaps not. It has become part of the landscape, a symbol whose meaning shifts depending on who is looking. For some, it represents the unity of science and spirituality, the recognition that ancient wisdom and modern knowledge can illuminate each other. For others, it represents the arrogance of science, the hubris of humans attempting to unlock secrets not meant to be known. For still others, it is simply a beautiful work of art, a bronze dancer frozen in eternal motion. The dance continues underground. Particles collide, new discoveries emerge. The cosmic cycle of creation and destruction plays out on the smallest scales imaginable. And above ground, people argue about what it all means. But the statue is not the only thing that has fueled suspicion of CERN. In the summer of 2016, a video emerged that seemed to confirm the darkest fears of conspiracy theorists. Filmed at night, in the courtyard where Nataraja dances, it appeared to show a group of robed figures performing a ritual sacrifice. The video was a hoax created by CERN employees as a joke, but it spread across the internet like wildfire, achieving millions of views and spawning countless follow-up videos claiming to reveal the truth about what happens at CERN after dark. In the next chapter, we will explore the conspiracy theories surrounding CERN in greater detail, from portals to hell to the Mandela effect to the strange theory that the laboratory has shifted our entire universe into an alternate timeline. Chapter 5: Portals to Hell. In the summer of 2022, the Large Hadron Collider roared back to life after a 3-year shutdown. Engineers had spent the hiatus upgrading the machine, preparing it for Run 3, a new phase of operations that would push the collider to its highest energies yet. For physicists, it was the beginning of an exciting new chapter in the exploration of fundamental physics. For conspiracy theorists, it was the end of the world. As the restart date approached, videos began appearing across social media warning of impending doom. The claims varied in their specifics but shared a common theme. CERN was about to open a portal. Depending on which video you watched, this portal might lead to another dimension, to the future, to hell itself, or to all three at once. The hashtag CERN trended globally. Posts warning friends and family to be ready for July 5th accumulated millions of views. Some urged preparation of emergency supplies, others recommended prayer. A few suggested that viewers should simply enjoy their final days before the scientists in Switzerland destroyed everything. "Be ready for July 5th, everyone," one viral tweet proclaimed. "That's all I'm saying. Protect your energy. Be alert. Don't do things that lower your vibration, your focus. CERN will be opening a portal." They began getting it ready when the planets aligned on June 24th. The reference to planetary alignment was not coincidental. In late June of 2022, 5 planets were visible in the pre-dawn sky in a rough line. This astronomical event, while visually striking, has no physical significance beyond the coincidental positions of objects millions of miles apart. But in the realm of conspiracy theory, coincidence becomes connection, and connection becomes causation. Others tied the CERN restart to the television show Stranger Things, which had recently released a new season featuring portals to an alternate dimension. The timing was coincidental, but the imagery was irresistible. Netflix released a show about scientists opening portals just weeks before CERN fired up their giant machine. To conspiracy theorists, this was not marketing synergy, but predictive programming, the entertainment industry warning the masses of what was to come. The specific claims about what CERN might unleash were remarkably varied. Some focused on black holes. While scientists do hope to someday detect microscopic quantum black holes at the LHC, such black holes would be unimaginably tiny and would evaporate instantly. They pose zero threat to Earth. But stripped of context, the phrase CERN is creating black holes sounds terrifying. Others focused on antimatter. CERN does produce and study antimatter, though in quantities so small that they could not power a light bulb, let alone destroy anything. The total amount of antimatter ever produced by humanity, across all laboratories, would not be enough to boil a cup of tea. But again, the word antimatter conjures images from science fiction of matter and energy weapons of apocalyptic power. The portal theory drew on a more fundamental misunderstanding. Some theoretical physicists have proposed that the universe might contain extra dimensions beyond the 3 spatial dimensions we experience. If these extra dimensions exist, the LHC might produce particles that briefly disappear into them before returning to our familiar dimensions. Detecting such particles would be a revolutionary discovery, but the key word is theoretical. There is currently no experimental evidence that extra dimensions exist. The LHC has been searching for signs of them since it began operation and has found nothing. Even if such dimensions do exist, and even if the LHC could interact with them, there is no mechanism by which this would create a doorway that humans or anything else could pass through. A particle briefly moving through an extra dimension is not a portal, yet the portal theory persists because it taps into something deeper than physics. The idea that hidden doorways exist between different realities is ancient and universal. Mythology and religion across cultures describe passages between the world of the living and the world of the dead, between the mundane and the divine. The portal theory maps modern scientific language onto this ancient template. The specific claim that CERN might open a portal to hell adds a religious dimension that resonates with many believers. The Book of Revelation describes an abyss from which demons emerge at the end times. Some interpret CERN's underground tunnels as a literal attempt to break through to this abyss. The statue of Shiva becomes an idol to demonic forces. The scientists become modern-day sorcerers. This interpretation requires ignoring what scientists actually say about their work. It requires treating scientific terminology as coded language for supernatural concepts. It requires viewing the open publication of results, the international collaboration of researchers, and the routine nature of daily operations as elaborate cover for hidden rituals. But for those already inclined to distrust scientific authority, these requirements pose no obstacle. The claim, about 6s hidden in the CERN logo, illustrates how determined searchers find patterns wherever they look. The CERN logo consists of interlocking shapes representing the paths of particles in early accelerators. The shapes curve and overlap in ways that, with sufficient imagination, can be seen to resemble the number 6 repeated 3 times. The fact that this interpretation requires ignoring what the shapes actually represent, particle trajectories recorded in experiments, does not diminish its persuasive power for believers. Some have also pointed out that the LHC tunnel is approximately 16.6 miles around, close to the number 16.7, but close enough for conspiracy purposes. Others note that CERN sits on the site of an ancient Roman town called Apolliacum, supposedly dedicated to Apollo, a god associated with destruction in some interpretations. The connections multiply, each one adding to the apparent pattern, each one reinforcing the conclusion already reached. Physicists at CERN have addressed these claims directly. Their FAQ section on social media queries is remarkably patient in its explanations. No, the LHC will not generate black holes in the cosmological sense. Yes, some theories suggest that microscopic quantum black holes might be possible, and observing such an event would be thrilling and perfectly safe. No, CERN is not opening portals to other dimensions. The LHC might discover evidence for extra dimensions, but that is completely different from creating a gateway. The organization emphasizes context. The collisions at the LHC, while high energy by human standards, occur routinely in nature. Cosmic rays from distant stars and galaxies strike Earth constantly, producing collisions with energies that exceed anything the LHC can achieve. The Moon, having no atmosphere to block cosmic rays, experiences such collisions continuously. The Sun, the Earth, and every other object in the solar system have been bombarded by particles far more energetic than anything from the LHC for billions of years. If such collisions could open portals or destroy planets, it would have happened long ago. But these explanations struggle to compete with the visceral appeal of conspiracy theories. A patient explanation of cosmic ray physics requires attention and effort to understand. A claim that CERN is opening a portal to hell requires only the willingness to believe. In the attention economy of social media, simplicity and emotion consistently win over complexity and nuance. The restart in July 2022 proceeded without incident. Beams circulated, collisions occurred, data flowed to the experiments, no portals opened, no demons emerged. The world continued to spin on its axis, orbiting the Sun as it had for billions of years. The absence of catastrophe did not deter the conspiracy theorists. Some claimed that something had happened, we just had not noticed it yet. Others argued that the portal was being opened gradually in stages to avoid detection. Still others proposed that the timeline had shifted, that we were now living in a parallel universe indistinguishable from our original one. This last theory connects to one of the most persistent conspiracy theories associated with CERN, the claim that the laboratory is responsible for the Mandela effect. The Mandela effect refers to the phenomenon of large groups of people sharing false memories of events that never happened. It takes its name from the observation that many people incorrectly remember Nelson Mandela dying in prison in the 1980s, when in fact he was released in 1990 and lived until 2013. Other examples of the Mandela effect include memories of the Berenstain Bears being spelled Berenstein, of the Monopoly Man having a monocle when he does not, of the movie character Darth Vader saying, "Luke, I am your father," when the actual line is, "No, I am your father." These false memories are fascinating psychological phenomena. Memory research has shown that human memory is far more malleable than we typically assume. We do not record events like a video camera. We reconstruct memories each time we recall them, and in that reconstruction, details can shift, merge with other memories, or be influenced by suggestions and expectations. But for some, the psychological explanation is unsatisfying. They propose instead that the discrepancies between memory and reality prove that reality itself has changed. In this view, those who remember Mandela dying in prison are not mistaken. They genuinely experienced a different timeline, one that has since been overwritten or merged with our current timeline. CERN enters this theory as the proposed mechanism for timeline shifts. The extreme energies of the LHC, the manipulation of fundamental particles, the recreation of Big Bang conditions, all of these are marshalled as evidence that the laboratory might be inadvertently or intentionally altering the fabric of space-time. Each new experiment is a potential moment of timeline disruption. Each strange memory is evidence of a universe subtly different from the one that existed before. Clara Nellist, a particle physicist who works on the Atlas experiment at CERN, has addressed these theories on social media. She posts educational videos explaining what the LHC actually does and debunking the most common misconceptions. In one video responding to claims about the Mandela effect, she simply states that the particle collider does not have the power to change reality or memories. The energies involved, while high in physics terms, are minuscule compared to the energy contained in everyday objects. But the theories persist. They form a self-reinforcing web where each element supports the others. The statue of Shiva proves malevolent intent. The logo contains hidden sixes. The portal claims are supported by the Mandela effect. The Mandela effect is caused by timeline shifts. The timeline shifts are caused by the LHC. And around it goes, each claim lending apparent credibility to the others. What drives people to believe these theories when scientific explanations are readily available? Psychologists point to several factors. Conspiracy theories offer simple explanations for complex phenomena. They provide a sense of special knowledge, the feeling of being among the few who truly understand what is happening. They give meaning to random events and uncertain feelings, and they often align with pre-existing distrust of authority, whether scientific, governmental, or both. For those who already suspect that powerful institutions are hiding the truth, CERN provides an irresistible target. It is large, well-funded, and engaged in activities that even educated laypeople struggle to understand. It uses terminology that sounds exotic and potentially ominous. It is located underground, invisible to ordinary observation. It is international, funded by governments that many conspiracy theorists already distrust. The irony is that CERN is among the most transparent scientific institutions on Earth. Its results are published openly. Its facilities are regularly toured by journalists, politicians, and members of the public. Its scientists give interviews, write blogs, and post on social media. The very misconceptions that conspiracy theories exploit are addressed directly in publicly available documents. But transparency is not enough when the audience has already decided what to believe. Denials become evidence of cover-up. Explanations become misdirection. Every attempt at education is filtered through a lens of suspicion that transforms it into further confirmation of the conspiracy. The portal theories represent the most dramatic end of the CERN conspiracy spectrum, but they are not the only claims circulating. In 2016, a video emerged that seemed to show something far more sinister than theoretical physics. A ritual sacrifice filmed at night in the courtyard where the statue of Nataraja stands. The video would be viewed millions of times, prompt an official investigation, and demonstrate how quickly fiction can become accepted as fact in the age of viral media. In the next chapter we will examine this video and the panic it caused, as well as the less sensational but no less persistent theory that CERN has shifted our collective reality into an alternate dimension where small details have been mysteriously changed. Chapter 6. The Mandela Effect and Alternate Dimensions. In 2010, a blogger named Fiona Broom attended a conference about paranormal phenomena. During a conversation with other attendees, she mentioned that she vividly remembered Nelson Mandela dying in a South African prison in the 1980s. She remembered seeing news coverage of his funeral on television. She remembered the grief and the tributes. There was only one problem. Nelson Mandela was still alive. He had been released from prison in 1990. He had become the first black president of South Africa. He had won the Nobel Peace Prize. He would not die until 2013. What surprised Broom was not that she had been mistaken. People misremember things all the time. What surprised her was that other people at the conference shared her false memory. They too remembered Mandela dying in prison. They too remembered the funeral coverage. They agreed on details that had never occurred. Broom coined the term Mandela effect to describe this phenomenon of shared false memories. She created a website to document examples, and the examples kept coming. People remembered the Berenstain Bears being spelled Berenstein. They remembered a movie called Shazam starring the comedian Sinbad as a genie, a movie that does not exist. They remembered the Monopoly man wearing a monocle. They remembered the evil queen in Snow White saying "Mirror, mirror on the wall," when the actual line is "Magic mirror on the wall." They remembered Curious George having a tail. Each of these memories was verifiably wrong, yet thousands, sometimes millions of people shared them. The phenomenon was undeniable. The explanation was disputed. Psychologists offered straightforward accounts, rooted in how memory actually works. Human memory is not a recording device. It is a reconstruction system. Every time we recall an event, we rebuild it from fragments, and in that rebuilding, details can shift. Suggestions from others can alter our memories. Expectations based on patterns can fill in gaps incorrectly. The Monopoly man seems like he should have a monocle, because monocles are associated with wealthy men from that era. Berenstein looks more like a typical name than Berenstain. These small errors propagate through culture as people discuss and reinforce each other's mistaken memories. But for many people, the psychological explanation felt inadequate. The memories were too vivid, too specific, too widely shared. Something else had to be happening. Enter CERN. The connection between the Large Hadron Collider and the Mandela effect emerged gradually on internet forums and blogs. The reasoning went something like this. The LHC manipulates the fundamental building blocks of reality. It recreates conditions from the Big Bang. It probes the deepest structures of space-time. What if, in doing so, it had accidentally shifted our reality into a parallel timeline? What if the people who remember Mandela dying in prison were not wrong but were recalling events from a previous version of reality that had since been overwritten? The theory had a seductive elegance. It explained why so many people shared the same false memories. They were not false memories at all, but real memories of a different timeline. It explained why the affected memories tended to be minor details rather than major events. A shift between closely parallel timelines would only produce small differences. It explained why the phenomenon seemed to be increasing over time. The LHC had been operating since 2008, plenty of time to accumulate timeline shifts. Of course, the theory also had problems that its proponents rarely addressed. The Mandela effect describes memories of events from before the LHC existed. Broom and others remembered Mandela dying in the 1980s, 2 decades before the collider was even built. If CERN was shifting timelines, why would it change events from the past? Believers had answers for this too. Perhaps time does not work the way we think. Perhaps a change to space-time propagates both forward and backward. Perhaps the act of observation itself, enabled by the LHC experiments, was what caused the shift. The explanations grew more elaborate as the objections mounted, each patch creating new wrinkles that required further patches. The theory spread rapidly on social media. YouTube videos titled "Proof CERN" shifted us to a parallel universe accumulated millions of views. Reddit forums dedicated to cataloguing Mandela effect examples buzzed with speculation about the LHC. TikTok creators posted breathless accounts of newly discovered discrepancies, each one attributed to CERN's meddling with reality. The scientists at CERN watched this unfold with a mixture of bemusement and concern. Bemusement because the claims were so far removed from what the LHC actually does. Concern because the misinformation was spreading faster than any correction could hope to catch. Particle physicist Clara Nellist became one of the most visible voices pushing back against the theories. Working on the Atlas experiment, she understood the actual capabilities and limitations of the machine. She began posting educational content on TikTok and other platforms, explaining in accessible language what the LHC can and cannot do. In one video, she addressed the Mandela effect directly. The LHC does not have the power to change memories or alter reality, she explained. The energies involved, while high from a particle physics perspective, are tiny compared to the energy contained in everyday objects. A single flying mosquito carries more energy than a proton in the LHC. The idea that colliding particles could somehow rewrite history or shift entire timelines has no basis in physics, but the debunking faced an uphill battle. Conspiracy theories are sticky in ways that scientific explanations are not. They offer the thrill of hidden knowledge, the satisfaction of seeing patterns that others miss, the comfort of simple answers to complex questions. A video explaining the psychology of false memory will never be as engaging as a video claiming that reality itself has been altered. The Mandela effect community continued to grow, documenting ever more examples of apparent discrepancies. Some of these were genuinely puzzling, at least until investigated. Changes in product packaging or corporate logos were attributed to timeline shifts when they were actually documented rebranding efforts. Misremembered movie lines were cited as proof of reality alteration when the actual films had always contained the correct lines. One of the most discussed examples involved the children's book series The Berenstain Bears. Millions of people remember the name being spelled Berenstein, with an EIN ending common to many Jewish surnames. The actual spelling is Berenstain, with an AIN ending that is less common. This discrepancy is often cited as the clearest evidence of a timeline shift. But the explanation is prosaic. The name Berenstain was the actual surname of the book's creators, Stan and Jan Berenstain. The unusual spelling was frequently misread and misremembered, especially by children who encountered the books before their reading skills were fully developed. Once the incorrect spelling was lodged in memory, it was reinforced by the expectation that names ending in that sound are usually spelled S-T-E-N. Similar explanations exist for virtually every Mandela effect example. The Fruit of the Loom logo never had a cornucopia, though the arrangement of fruit resembles depictions of cornucopias. The evil queen in Snow White has always said magic mirror, though mirror mirror has become the commonly quoted version through cultural transmission. Curious George never had a tail, though monkeys are associated with tails and the absence of one is easily forgotten. None of these explanations satisfy the true believers. For them, the very mundaneness of the explanations is suspect. Of course the authorities would claim that the discrepancies are just memory errors. Of course the evidence would be scrubbed from records. That is exactly what you would expect if reality had been altered. This unfalsifiability is both the strength and the weakness of the theory. It cannot be disproven because any evidence against it can be reinterpreted as evidence for it. But by the same token, it cannot be proven because it makes no testable predictions. It exists in a realm beyond scientific inquiry, a matter of faith rather than evidence. The connection to CERN adds a veneer of scientific plausibility to what is essentially a supernatural claim. By invoking particle physics, timeline shift theorists can claim that their ideas are grounded in cutting-edge science. They point to real concepts like the multiverse, which some theoretical physicists have proposed to explain features of quantum mechanics and cosmology. If physicists believe in parallel universes, why should it be crazy to think we might have shifted from one to another? The answer is that the multiverse, as proposed by physicists, is fundamentally different from the parallel timelines of Mandela effect theory. In most multiverse proposals, the different universes are completely separate from one another. There is no mechanism for moving between them, no way for changes in one to affect another. The universes exist as solutions to equations, not as places you can travel to or from. More importantly, the multiverse is a hypothesis, not an established fact. Many physicists are skeptical of it precisely because it seems to be unfalsifiable. Proposing that CERN can shift us between universes compounds speculation upon speculation, building a tower of assumptions with no foundation in observed reality. Yet the theory persists and spreads. Every time CERN announces a new experiment or achieves a new milestone, social media fills with speculation about what timeline shifts might result. Every newly noticed Mandela effect example is attributed to recent LHC operations. The theory has become self-sustaining, generating its own evidence through the act of looking for discrepancies. The psychological appeal is clear. We live in a world that often feels chaotic and meaningless. Major events seem to happen for no reason. Personal memories fade and change in ways that are disturbing to contemplate. The Mandela effect theory offers an alternative. Our memories are not failing us. Reality itself is shifting. We are not powerless observers of random change, but participants in a cosmic drama. Witnesses to manipulation by forces beyond our understanding. CERN serves as the perfect villain in this drama. It is large, mysterious, and engaged in activities that few people fully understand. It operates underground, hidden from view. It is funded by governments that many people already distrust. It uses terminology that sounds both scientific and ominous. It represents the pinnacle of human ambition to understand and control nature. If something strange is happening to reality, who better to blame than the people smashing atoms together beneath the mountains of Switzerland? The irony is that if timeline shifts were real, scientists at CERN would be among the most interested parties. Detecting evidence of parallel universes would be one of the greatest discoveries in the history of physics. Researchers would line up to study such a phenomenon. Papers would be published. Nobel Prizes would be awarded. Instead, the Mandela effect remains a curiosity of internet culture, a fascinating example of how memory and belief interact, how scientific terminology can be appropriated for unscientific purposes, and how conspiracy theories spread in the age of social media. The timeline shift theory is not the only CERN-related conspiracy that gained traction in the 2010s. In 2016, a video emerged that seemed to provide visual evidence of something far more sinister than altered memories. Robed figures, a ritual sacrifice, all filmed in the shadow of the Shiva statue. The video was fake, but its effects were very real. In the next chapter, we will examine the ritual video hoax, how it was created, why it spread so far so fast, and what it reveals about the intersection of science, media, and belief in the modern world. Chapter 7. The Ritual Video. The video appeared on YouTube in August of 2016. Shot at night from what appeared to be a window overlooking a courtyard, it showed a scene that seemed to confirm the darkest fears about CERN. A group of figures in dark robes surrounded the statue of Shiva. They moved in deliberate patterns. In the center, a woman in a white robe lay on the ground. One of the robed figures raised something that glinted in the low light. The figure brought it down. The woman went still. The person filming cursed, screamed, and ran. Within days, the video had been viewed millions of times. Conspiracy websites proclaimed it proof that satanic rituals were being performed at CERN. Religious commentators pointed to it as evidence of demonic activity. Social media exploded with speculation about what dark forces the scientists had summoned. The video was titled "Murder at CERN." Some versions added subtitles alleging that this was proof of human sacrifice at the world's most powerful physics laboratory. Screenshots circulated on Facebook, Twitter, and countless forums. Each share added another layer of interpretation, another claim of authenticity, another warning about the evil lurking beneath Geneva. CERN was forced to respond. A spokesperson confirmed to Agence France Presse that the video had been filmed on CERN property but stated unequivocally that it was a prank. "These scenes were filmed on our premises without official permission or knowledge," the spokesperson said. CERN does not condone this type of spoof, which can give rise to misunderstandings about the scientific nature of our work. The statement confirmed what many had suspected. The figures in the video were CERN employees or visiting researchers. They had used their access badges to enter the campus at night. They had staged a fake ritual in front of the Shiva statue, knowing full well what reaction it would provoke. And one of them had filmed it from a window, adding the running and screaming for dramatic effect. CERN launched an internal investigation. The exact identities of those involved were never publicly disclosed, but the organisation confirmed that they had been identified and that appropriate measures had been taken. The statement emphasised that while CERN welcomes thousands of scientists and visitors, each year this kind of behaviour breached professional guidelines. The prank had been intended as dark humour, a way of poking fun at the conspiracy theories that had swirled around CERN for years. The participants apparently thought it would be obvious that the video was fake. They underestimated how desperately some people wanted to believe it was real. To understand why the video spread so far and so fast, you have to understand the ecosystem it entered. By 2016, conspiracy theories about CERN had been building for nearly a decade. The portal theories, the Mandela effect claims, the Shiva statue interpretations had all laid the groundwork. A community of believers existed, constantly searching for new evidence to support their views. The ritual video was the evidence they had been waiting for. The found footage style of the video added to its apparent authenticity. The shaky camera work, the poor lighting, the genuine seeming panic of the person filming all mimicked the aesthetic of real amateur video capturing unexpected events. Horror movies like The Blair Witch Project and Paranormal Activity had trained audiences to associate this visual style with reality. The setting amplified the impact. The video was clearly filmed at CERN. The Shiva statue was recognisable. The architecture matched photographs and videos of the campus. This was not some random location that could be anywhere. This was the actual place where scientists were supposedly tampering with the fabric of reality. The timing also played a role. The video emerged during a period of heightened distrust in institutions of all kinds. Political polarisation was increasing. Fake news was becoming a dominant topic of discussion. Social media algorithms were optimizing for engagement, and nothing engages like outrage and fear. The video was perfectly designed to exploit these conditions. What is remarkable is how little the debunking mattered. CERN confirmed it was a prank. News. Organizations reported that it was staged. Fact-checking websites published detailed analyses explaining how the video was made and why it was obviously fake. None of this stopped the spread. True believers had ready explanations. Of course, CERN would claim it was a prank. What else would they say? The fact that they launched an investigation proved that something really happened. The identified employees were probably scapegoats, punished not for staging a hoax but for exposing the truth. Every denial became further evidence of cover-up. Some conspiracy theorists went further, arguing that the prank explanation was itself a cover story. They claimed that real rituals were being performed at CERN, and when footage accidentally leaked, the organisation decided the safest response was to admit the video existed, but claim it was just employees joking around. By acknowledging the footage while denying its significance, CERN could diffuse the situation without actually explaining what was happening. This interpretation required ignoring the obvious fact that the video was staged. The acting was mediocre at best. The stabbing motion was clearly pantomimed. No blood was visible despite the apparent violence. The woman on the ground lay perfectly still rather than reacting to being attacked. The person filming screamed and ran rather than calling for help or trying to intervene. Every detail pointed to a staged production rather than a genuine crime. But for those who wanted to believe these objections could be explained away. Perhaps the ritual was symbolic rather than literal. Perhaps the woman was a willing participant in a ceremony rather than a victim. Perhaps the footage had been edited to remove the most disturbing elements. Perhaps the poor quality of the acting was itself a form of misdirection. The ritual video illustrates a broader truth about conspiracy theories in the digital age. Evidence matters less than narrative. When a piece of content confirms what people already believe, they accept it readily. When evidence contradicts their beliefs, they dismiss it as manufactured or misinterpreted. The video was fake, but it became real in its effects because enough people chose to treat it as real. CERN has continued to deal with the fallout from the video years after the fact. It still appears in conspiracy content, often presented as if it were genuine footage rather than a debunked hoax. New viewers encounter it without context and assume it shows what it appears to show. The same images circulate again and again, each cycle generating fresh outrage. The organisation has tried to address the issue through transparency and education. Their website includes a section addressing common misconceptions. They conduct regular tours and welcome journalists to see their facilities. They post explanatory content on social media. Scientists like Clara Nellist engage directly with conspiracy claims, patiently explaining the actual science. But the asymmetry is daunting. A single viral video can reach millions of people in hours. A debunking post reaches a fraction of that audience, and often only reinforces skepticism among those already inclined to disbelieve. The truth moves slowly while lies travel at the speed of light. The ritual video also raised questions about the culture at CERN. How did it happen that employees thought this was a good idea? What does it say about the atmosphere at the laboratory, that staging a fake human sacrifice in front of a Hindu deity seemed like acceptable humour? Some defenders argued that the prank reflected the dark humour common among scientists dealing with stressful, high-stakes work. Physicists routinely joke about topics that outsiders might find inappropriate. Gallows humour is a way of coping with the pressure of the job and the isolation of spending long hours underground with complex machines. Others suggested that the prank was a misguided attempt to confront the conspiracy theories head-on. By creating an obviously fake ritual video, the perpetrators may have thought they were exposing the absurdity of the claims. If believers would accept something this ridiculous as proof, it would reveal how low their standards of evidence really were. If that was the intent, it backfired spectacularly. Rather than exposing the foolishness of conspiracy thinking, the video provided fresh ammunition for believers. It became one of the most cited pieces of evidence for dark activities at CERN, referenced in countless videos, articles, and social media posts for years afterward. The incident highlights the difficulty institutions face when dealing with conspiracy theories. Ignoring them allows misinformation to spread unchallenged. Addressing them directly can lend them unwarranted credibility. Attempting humour or satire can be misinterpreted and cause the exact problems it was meant to prevent. There are no easy answers. CERN ultimately chose a policy of patient engagement. They answer questions. They provide information. They try to educate the public about what they actually do. They acknowledge that conspiracy theories exist without dignifying the most extreme claims with detailed rebuttals. Whether this approach will succeed in the long run remains to be seen. The ritual video has faded somewhat from public attention as newer controversies have emerged, but it remains a cautionary tale about the unpredictable dynamics of viral content. A few employees playing a prank created footage that would be viewed tens of millions of times and become part of the permanent folklore surrounding one of the world's most important scientific institutions. Meanwhile, the actual science at CERN continued without interruption. While conspiracy theorists debated fake rituals and imagined portals, physicists were making real discoveries that genuinely advanced human understanding of the universe. The contrast between the fevered speculation and the methodical reality could not have been sharper. In the next chapter, we will turn from fiction to fact and examine what CERN actually discovered in 2025. Record-breaking experiments, new observations of rare particle decays, and hints of physics beyond the standard model. The truth, it turns out, is more fascinating than any conspiracy theory. Chapter 8. What they actually found. While conspiracy theorists speculated about portals and timeline shifts, scientists at CERN were doing what they have always done: running experiments, collecting data, making discoveries that actually advance human knowledge. The year 2025 proved to be one of the most productive in the laboratory's history. The numbers alone tell a story of remarkable achievement. In November, the Large Hadron Collider completed its proton physics run for the year with integrated luminosity of 125.4 inverse femtobarns delivered to the ATLAS and CMS experiments. This exceeded the target and surpassed the previous year's record, despite having fewer operating days. The machine was simply performing better than ever before. To understand what these numbers mean, consider that each inverse femtobarn represents approximately 80 trillion proton-proton collisions. The LHC delivered the equivalent of 10 quadrillion collisions to each major experiment in a single year. Every one of those collisions is a chance to observe rare physics, to catch a glimpse of particles that exist for only the tiniest fraction of a second before decaying into other particles. The cumulative achievement is even more impressive. Since the LHC began operations, ATLAS and CMS have each recorded 500 inverse femtobarns of integrated luminosity. That is 50 million billion particle collisions, each one recorded and analysed by sophisticated detectors and computers. The dataset is unprecedented in the history of physics, but 2025 was not just about doing more of the same. For the first time ever, the LHC collided oxygen and neon ions. Previous heavy ion runs had focused on lead, the heaviest practical ion source. The lighter oxygen and neon ions opened new windows into nuclear physics. The results came quickly. Studies of the neon collisions confirmed something remarkable about the shape of neon nuclei. They are not spherical as simple models would suggest. Instead, neon nuclei are elongated, shaped like bowling pins. This deformation affects how the nuclei interact and helps physicists understand the forces that bind protons and neutrons together. The oxygen collisions provided complementary data, probing a different regime of nuclear physics. All 4 major LHC experiments participated in these special runs, each bringing their unique capabilities to bear on the new collision types. ALICE, which specializes in heavy ion physics, achieved a data-taking efficiency of over 95% during the runs. The Higgs, boson discovered in 2012, remained a focus of intense study. The ATLAS collaboration announced new results at the European Physical Society conference in Marseille. They had found evidence, though not yet at discovery-level significance, that the Higgs boson decays into muons. This might sound like a minor technical detail, but it represents years of painstaking work. The Higgs decays into muons only about 1 in every 5,000 times. Detecting this rare process against the overwhelming backgrounds of other physics requires enormous amounts of data and exquisite control of systematic uncertainties. More importantly, the muon decay channel provides a window into the second generation of matter particles. Previous Higgs measurements had focused on decays to heavier third-generation particles, like tau leptons and bottom quarks. Observing the muon decay confirms that the Higgs field interacts with lighter particles in the expected way, another test passed by the standard model. The experiments also improved their sensitivity to even rarer Higgs decays. The decay of a Higgs boson into a Z boson and a photon is predicted to occur only a tiny fraction of the time, through a complicated quantum mechanical process involving virtual particles. Any deviation from the predicted rate would indicate new physics, particles, or forces not included in the standard model. So far, no such deviation has been found. The measurements are consistent with standard model predictions. This is both a triumph and a frustration. A triumph because it validates decades of theoretical work. A frustration because physicists are eager to find something new, some crack in the standard model that would point toward deeper understanding. The search for dark matter continued without definitive success, but with increasingly tight constraints. The ATLAS collaboration released a comprehensive review of their supersymmetry searches, examining millions of possible scenarios for dark matter particles. While no evidence of supersymmetric dark matter was found, the search ruled out large swaths of previously possible parameter space. This kind of negative result might seem disappointing, but it is genuinely valuable. Knowing where dark matter is not helps narrow the search for where it might be. The excluded regions push theorists toward new models, and experimentalists toward new search strategies. Science advances by ruling out possibilities as well as by confirming them. Other experiments at CERN contributed their own discoveries. The NANG62 and NA64 experiments, located in the north area rather than at the LHC, searched for dark bosons, hypothetical particles that could mediate interactions between ordinary matter and dark matter. They place the most stringent limits yet on certain dark matter models, closing doors that future experiments will not need to knock on. The Alpha experiment continued its studies of antimatter. Researchers have been creating and trapping antihydrogen atoms, the antimatter equivalent of ordinary hydrogen, and comparing their properties to those of regular hydrogen. Any difference would be a sign of physics beyond the standard model. So far, antimatter and matter appear to be perfect mirror images of each other, deepening the mystery of why the universe contains matter at all. One of the most striking results of the year came from an analysis of how matter forms in the extreme conditions created by heavy ion collisions. When lead nuclei collide at LHC energies, they create a quark-gluon plasma, a state of matter that existed microseconds after the Big Bang. As this plasma cools, it condenses into ordinary particles like protons and neutrons. But physicists had long been puzzled by the presence of deuterons and antideuterons in this plasma. Deuterons are nuclei containing one proton and one neutron, held together by a relatively weak force. Under the extreme temperatures of the quark-gluon plasma, these delicate structures should fall apart almost instantly. Yet experiments kept detecting them. The answer, published in late 2025, was elegant. The deuterons were not surviving the plasma. They were forming later, after things had cooled down, from the decay of heavier short-lived particles called resonances. This explains about 90% of the observed deuterons and antideuterons, solving a mystery that had puzzled physicists for years. Understanding this process matters beyond pure curiosity. Antideuterons detected in cosmic rays could be a signature of dark matter annihilation in space. But interpreting that signal requires understanding how many antideuterons are produced by ordinary astrophysical processes. The CERN result provides crucial input for these calculations. The experiments also tested the boundaries of their detectors with special high pile-up runs. Pile-up refers to multiple collisions occurring simultaneously when the proton bunches cross. Normal LHC operations produce about 60 simultaneous collisions. The test runs pushed this to around 150, simulating conditions expected when the high luminosity upgrade is complete. The detectors handled the increased complexity remarkably well. New trigger systems designed to identify interesting events amid the overwhelming flood of data performed as intended. Machine learning algorithms helped separate signal from background with unprecedented precision. The tests validated years of preparation for the more challenging conditions to come. In April of 2025, the 4 major LHC collaborations received the Breakthrough Prize in Fundamental Physics. The prize, one of the most lucrative in science, recognized the thousands of researchers who had contributed to discoveries at the collider. The $3 million award would be donated to the CERN Society Foundation, funding doctoral research opportunities for students from around the world. The Director General of CERN, Fabiola Gianotti, expressed pride in the recognition. Thousands of people at CERN contribute daily to pushing the boundaries of human knowledge, she said. The Breakthrough Prize underlines CERN's importance as a model of peaceful collaboration in science and technology development. This collaboration is perhaps CERN's most remarkable achievement. Scientists from nations that are geopolitical rivals work side by side on the same experiments. Researchers from over 100 countries contribute to the LHC program. Decisions are made by consensus. Results are shared openly with the world. In an era of increasing nationalism and conflict, CERN represents an alternative model of how humans can work together. The science continues to unfold. Each year brings new data, new analyses, new results. The standard model has been tested to extraordinary precision and continues to hold. But physicists are certain that it is not the final word. Dark matter exists but does not appear in the model. Gravity is not included. The values of particle masses seem arbitrary rather than explained. Somewhere in the data already collected or yet to be recorded, there may be clues pointing toward a deeper theory. The Higgs boson itself might be a portal to new physics if its properties differ even slightly from predictions. Rare decays might reveal new particles too heavy to produce directly. Subtle asymmetries might explain why we exist at all. The search requires patience. The LHC will continue operating through 2026 before entering a long shutdown for the high luminosity upgrade. When it returns in 2030, it will be a more powerful machine, capable of producing 5 times more collisions per second. The experiments will have new detectors, new triggers, new analysis techniques. And beyond the high-luminosity LHC lies something even more ambitious. A machine that would dwarf the current collider, a tunnel 3 times as long, energies 7 times higher, a physics program extending into the 2070s and beyond. The Future Circular Collider represents the next great leap in humanity's exploration of fundamental reality. But before we look to that future, we should acknowledge what CERN has already given the world beyond particle physics. The World Wide Web, invented at CERN in 1989, transformed human civilization. Medical technologies developed for particle detectors now save lives in hospitals. The model of open international collaboration has inspired institutions around the globe. In the next chapter, we will explore these gifts that extend far beyond the tunnel walls, the ways that CERN's quest to understand the universe has changed everyday life for billions of people who will never hear of a Higgs boson or a quark-gluon plasma. Chapter 9. The Gift That Changed the World. In 1989, a British computer scientist named Tim Berners-Lee was frustrated. He worked at CERN, surrounded by some of the most brilliant physicists on Earth, all struggling with a mundane problem. They could not easily share information. CERN was then, as now, a place where scientists from around the world came together to collaborate on experiments. These researchers came from different universities, different countries, different computing systems. They used different software, different file formats, different ways of organizing data. Getting information from one computer to another was a constant headache. Berners-Lee had an idea. What if there was a universal way to link documents stored on different computers? What if you could click on a word in one document and be taken instantly to a related document on a completely different machine, perhaps on another continent? What if all the information in the world could be connected in a web of links? In March of 1989, he submitted a proposal to his supervisor. The document was titled Information Management, A. Proposal. His supervisor, Mike Sendall, wrote on the cover page vague but exciting. It was perhaps the most consequential marginal note in history. Berners-Lee got permission to work on his idea. By the end of 1990, he had created the essential technologies that would become the World Wide Web. He invented HTML, the language used to create web pages. He invented HTTP, the protocol that allows web browsers to request pages from web servers. He invented URLs, the addresses that identify locations on the web. He built the first web browser and the first web server, running on a Next computer in his office at CERN. The first website went live on August 6, 1991. It explained what the World Wide Web was and how to use it. The page still exists, preserved as a piece of digital history. It is simple by modern standards, just text and links, but it represents the birth of something that would reshape human civilization. At first, the web grew slowly. Other research institutions connected their computers. Universities set up websites. The community of users expanded from hundreds to thousands, but it was still mainly a tool for academics and technologists. Then in 1993, CERN made a decision that would change everything. The organization announced that the World Wide Web technology would be available to everyone, royalty-free, forever. There would be no patents, no licensing fees, no restrictions on use. The web would belong to humanity. This decision was not inevitable. CERN could have tried to profit from its invention. The potential value was already becoming apparent. Commercial interests were circling. But the leadership at CERN understood that the web's potential could only be realized if it was truly open. A web controlled by any single entity, whether a company or a government or even CERN itself, would never achieve universal adoption. The decision reflected CERN's founding principles. Article 2 of the CERN Convention states that the results of experimental and theoretical work shall be published or otherwise made generally available. The web was not a physics result, but it was a product of CERN's culture of openness. Keeping it proprietary would have violated the spirit of the institution. Tim Berners-Lee left CERN in 1994 to found the World Wide Web Consortium at MIT, the organization that continues to oversee web standards today. He has spent the decades since advocating for an open, accessible web and warning against the concentration of power in large platforms. In 2017, he received the Turing Award, often called the Nobel Prize of Computing, for inventing the web. The impact of the World Wide Web is almost impossible to overstate. It transformed commerce, creating trillion-dollar companies and destroying entire industries. It transformed communication, enabling instant connection across any distance. It transformed politics for better and worse. It transformed entertainment, education, journalism, and virtually every other domain of human activity. All of this traces back to a frustrated computer scientist at a physics laboratory trying to help colleagues share information more easily. The most revolutionary technology of the late 20th century was essentially a side project at CERN. But the web is not the only gift CERN has given to the world beyond physics. The technologies developed to build and operate particle accelerators have found applications in medicine, industry, and daily life. The flow of innovation from fundamental research to practical application is constant and often surprising. Consider medical imaging. Positron emission, tomography, or PET scanning, uses the same type of particle interactions that physicists study at CERN. In a PET scan, a patient is injected with a radioactive tracer that emits positrons, the antimatter counterpart of electrons. When a positron meets an electron, both particles annihilate, producing gamma rays that detectors can pick up. By tracking these gamma rays, doctors can create detailed images of metabolic activity inside the body. The technology for detecting these gamma rays draws heavily on particle physics. The scintillating crystals that convert gamma rays to visible light, the photodetectors that measure the light, the electronics that process the signals, all of these were developed for and refined by particle physics experiments. CERN's crystal-clear collaboration has been particularly important in advancing PET technology. The group developed lead tungstate crystals for the CMS detector at the LHC. These same crystals have been adapted for medical imaging, enabling more sensitive and precise PET scanners. The ClearPen project created a dedicated breast cancer scanner that can detect tumours as small as 1.3 millimeters. Cancer treatment has also benefited from particle accelerator technology. Proton therapy uses beams of protons to destroy tumours with greater precision than conventional radiation. The protons can be tuned to deposit most of their energy at a specific depth, destroying cancer cells while sparing surrounding healthy tissue. CERN has actively contributed to this field. The PIM study, led by CERN in the 1990s, designed a proton synchrotron specifically for medical applications. Several facilities around Europe were built based on this design. CERN also hosts the OpenMed project, which helps develop next-generation particle therapy techniques. Even more experimental is the use of antiprotons for cancer treatment. In 2006, researchers at CERN's antiproton cell experiment announced that antiprotons were 4 times more effective than protons at killing cancer cells. When an antiproton annihilates with matter at the end of its path, it releases additional energy right at the tumor site. While antiproton therapy remains years from clinical use, the research continues. The superconducting magnet technology developed for particle accelerators has found applications in MRI machines. The powerful, stable magnetic fields needed to guide particles around accelerator rings are similar to those needed to image soft tissue in the human body. Advances in superconducting materials and cryogenic systems at CERN have filtered down to medical device manufacturers. Beyond medicine, CERN technology appears in unexpected places. The touchscreens on modern smartphones descend from technology developed for particle physics experiments. The distributed computing networks that analyze LHC data pioneered techniques now used by cloud computing services worldwide. Even the timing systems that synchronize particle bunches in accelerators have applications in telecommunications and financial trading. The model of international collaboration that CERN represents has perhaps been as influential as any specific technology. When the laboratory was founded in 1954, the idea that former enemies could work together on peaceful science seemed radical. Today it is taken for granted. CERN's success has inspired similar collaborations in other fields, from astronomy to genomics. The economic impact is substantial and quantifiable. Studies have estimated that for every euro invested in CERN, multiple euros return to the economy through technological spin-offs, trained personnel, and industrial contracts. Companies that work with CERN on technical challenges develop expertise that they apply to other projects. Students who train at CERN carry their skills into careers across many sectors. CERN also serves as a beacon for science education and public engagement. Hundreds of thousands of people visit the laboratory each year. Many more engage through online resources, virtual tours, and educational programs. The organisation has invested heavily in communicating not just its results, but the process of scientific discovery itself. This outreach matters more than ever in an age of misinformation. When CERN scientists take the time to explain their work on social media, they are not just correcting conspiracy theories. They are demonstrating what science looks like in practice. They are showing that scientific knowledge is hard-won through careful observation and rigorous testing, not received from authority or invented to serve hidden agendas. The contrast with the conspiracy theories could not be sharper. CERN actually publishes its results for anyone to examine. It actually invites visitors to tour its facilities. It actually answers questions from the public about its work. The transparency is not a facade hiding secret activities. It is the fundamental operating principle of an institution dedicated to expanding human knowledge. Tim Berners-Lee could not have imagined what the web would become when he wrote his proposal in 1989. The physicists who founded CERN in 1954 could not have imagined the discoveries their successors would make. Science proceeds by accumulation, each generation building on the work of those who came before, often in directions no one anticipated. The same principle applies to the future. Whatever comes from CERN's work in the coming decades will likely include surprises, technologies not yet imagined, discoveries that reshape our understanding, applications that transform daily life in ways we cannot predict. That future is already taking shape in planning documents and preliminary studies. The high luminosity upgrade to the LHC will extend the machine's capabilities through the 2030s. Beyond that, something far more ambitious is under consideration. A new accelerator that would make the LHC look modest. A tunnel 91 kilometers around. Energies 7 times higher than anything achieved before. In the final chapter, we will explore this vision of the future circular collider, the machine that might succeed the LHC, and the questions it hopes to answer about the deepest mysteries of the universe. Chapter 10. The 90-kilometer machine. The Large Hadron Collider is the largest machine ever built by human beings. Its tunnel stretches 27 kilometers beneath the Swiss and French countryside. Its magnets weigh tens of thousands of tons. Its detectors are the size of apartment buildings. For nearly 2 decades, it has defined the frontier of particle physics. And yet, even before the LHC began operating, scientists were already planning its successor. The future circular collider would make the LHC look like a warm-up act. The proposed tunnel would stretch 91 kilometers in circumference, more than 3 times the size of the current machine. It would pass beneath Lake Geneva, under the Jura Mountains, through rock formations that were old when dinosaurs walked the Earth. At its deepest points, the tunnel would lie 400 meters underground. The project would unfold in 2 phases, spanning most of the 21st century. First would come the FCCEE, an electron-positron collider. Unlike the LHC, which smashes protons, this machine would collide electrons with their antimatter counterparts. These cleaner collisions would allow precision measurements of known particles, especially the Higgs boson, to unprecedented accuracy. Then, perhaps in the 2070s, the electron-positron machine would give way to the FCCHH, a proton-proton collider. This second phase would push to energies of 100 trillion electron volts, 7 times higher than the current LHC. At such energies, entirely new phenomena might reveal themselves. Particles too heavy to create today might spring into existence. The mysteries of dark matter and dark energy might finally yield to direct investigation. The estimated cost is 15 billion Swiss francs for the first phase alone. Construction could begin in the early 2030s if approved. The machine would operate well into the second half of the century, potentially running until the year 2090 or beyond. The scientists who plan it today may never see its greatest discoveries. In November of 2025, the CERN Council took a crucial step forward. After reviewing the completed feasibility study, the Council endorsed the FCC project as technically viable and free of major obstacles. This was not yet approval to build, but it was a green light to continue planning, to refine cost estimates, to engage with governments and funding agencies. The next decision point will come around 2028. By then, the European strategy for particle physics will have been updated, providing guidance on the community's priorities. If the strategy endorses the FCC, and if member states commit funding, construction could begin on schedule. The physics case for such a machine rests on what we do not know. The standard model of particle physics is extraordinarily successful. It predicted the Higgs boson decades before its discovery. It explains the behavior of particles in experiments with exquisite precision, but it is clearly incomplete. The Standard Model does not explain dark matter, the invisible substance that holds galaxies together. Astronomical observations show that visible matter accounts for only about 5% of the universe's total mass and energy. Dark matter makes up another 27%. The remaining 68% is dark energy, an even more mysterious component that drives the accelerating expansion of space. None of this is explained by the Standard Model. The Standard Model also does not explain why the universe contains matter at all. According to the equations, equal amounts of matter and antimatter should have been created in the Big Bang. They should have annihilated each other, leaving nothing but radiation. Something broke the symmetry, favouring matter over antimatter by 1 part in a billion. That tiny imbalance allowed galaxies, stars, planets, and life to exist. But what caused it remains unknown. The Higgs boson itself presents puzzles. The mass of the Higgs is about 125 billion electron volts, a value that seems arbitrary. Some theoretical considerations suggest it should be much larger. The fact that it is not implies either extraordinary coincidence or some deeper principle we do not yet understand. The FCC would attack these mysteries from multiple angles. The precision measurements of the electron-positron phase would test whether the Higgs boson behaves exactly as the Standard Model predicts, or whether subtle deviations point to new physics. The high-energy proton collisions of the second phase would search directly for new particles that might comprise dark matter or explain the matter-antimatter asymmetry. The technical challenges are formidable. The FCCCH would require magnets producing fields of 16 Tesla, nearly twice as strong as those in the current LHC. Such magnets do not yet exist at the required scale. Developing them is a major focus of ongoing research and development, involving laboratories and industries around the world. The civil engineering alone would be a massive undertaking. Boring a 91-kilometre tunnel through the rock and soil beneath Geneva and the surrounding region would take years. 8 surface sites would be needed for access shafts, experiment halls, and support infrastructure. The environmental impact must be carefully managed, with plans already underway for reusing the millions of tons of excavated material. Power consumption is another concern. The FCCE would use between 1.1 and 1.8 terawatt-hours of electricity per year depending on its operating mode. This is comparable to a small city. Ongoing research aims to reduce consumption through more efficient technologies, and plans include recovering waste heat to supply heating for nearby communities. Not everyone in the physics community supports the FCC. Some argue that the era of ever larger colliders should end, replaced by smaller, more targeted experiments. They point to the diminishing returns of the LHC, which has confirmed the Standard Model rather than overturning it. They suggest that the billions of euros required might be better spent on other scientific priorities or on addressing more immediate human needs. These critics raise legitimate questions. There is no guarantee that the FCC would find new physics. The energy frontier might not be where the answers lie. Dark matter particles, if they exist, might be too light or too weakly interacting for even the FCC to produce. The return on investment, measured in fundamental discoveries, is genuinely uncertain. Supporters respond that fundamental science has never offered guaranteed outcomes. The value of the LHC was uncertain before it ran, yet it produced the Higgs discovery and countless other results. The value of building accelerators at all was uncertain in the early 20th century, yet they led to discoveries that transformed our understanding of nature and enabled technologies that define modern life. Moreover, the FCC would not just be a physics experiment. It would drive advances in superconducting materials, cryogenic systems, computing, and precision engineering. It would train thousands of scientists and engineers who would carry their expertise into other fields. It would represent a continued commitment to international scientific collaboration at a time when such collaboration is increasingly threatened by political tensions. In December of 2025, something unprecedented happened. A consortium of private donors pledged €860 million to support the FCC. The donors included the Breakthrough Prize Foundation, the Eric and Wendy Schmidt Fund for Strategic Innovation, and entrepreneurs John L. Cann and Xavier Neal. It was the first time in history that private philanthropists had offered to help build a major particle accelerator. Fabiola Gianotti, the Director General of CERN, expressed gratitude for the support. Their generosity and vision are essential to the prospective realization of the FCC and to enabling future generations of scientists to push the frontiers of scientific discovery and technology, she said. The private funding will not cover the full cost, which remains primarily the responsibility of CERN member states. But it signals that the project has support beyond the traditional physics community. It suggests that people outside the field see value in pushing the boundaries of human knowledge, even when the practical returns are uncertain. The decision to build or not to build will ultimately rest with governments. The physics community can advocate. Private donors can contribute, but the billions of euros required will come from public budgets, approved by parliaments and congresses, justified to voters who may never understand what a Higgs boson is or why finding one matters. This has always been the bargain of fundamental science. Society invests resources in pursuit of knowledge that may not pay practical dividends for decades, if ever. The investment is an act of faith in the value of understanding, a commitment to the idea that knowing how the universe works is worthwhile in itself. CERN has embodied this bargain for 70 years. From the ashes of World War II, European nations came together to build something dedicated entirely to peaceful understanding. They created an institution that has expanded human knowledge, developed transformative technologies, and demonstrated that international cooperation is possible even among former enemies. The Large Hadron Collider will continue operating through 2026 before entering a long shutdown for upgrades. When it returns as the high-luminosity LHC in 2030, it will be more powerful than ever. Scientists will continue searching for dark matter, for deviations from the standard model, for any hint of physics beyond our current understanding. If all goes according to plan, construction of the future circular collider could begin in the mid-2030s. The first electrons and positrons could circulate in the mid-2040s. The proton-proton phase might begin in the 2070s. The program could extend to the end of the century, spanning the careers of scientists not yet born. The conspiracy theories will likely continue as well. Every new experiment will spawn new speculation about portals and timeline shifts and demonic forces. The statue of Shiva will continue to feature in viral videos warning of dark intentions. The gap between what CERN actually does and what some believe it does will probably never close completely, but that gap matters less than it might seem. Science has always proceeded despite misunderstanding and opposition. Galileo faced the Inquisition. Darwin was caricatured as an ape. Einstein was accused of undermining the moral order. The truth eventually prevailed because reality has a way of asserting itself, experiment by experiment, discovery by discovery. 100 meters beneath the mountains, particles will continue to collide, data will continue to flow, scientists from around the world will continue to analyze and argue, and occasionally celebrate when nature yields another of her secrets. Who paid for this dream? The taxpayers of 25 member nations and more, the scientists who dedicated their careers, the engineers who solved impossible problems, the visionaries who looked beyond the rubble of war and imagined a place where humanity could work together to understand the universe. Who pays for this dream? We all do. And what we receive in return is knowledge. The knowledge that the universe operates according to laws we can discover. The knowledge that particles and forces and fields underlie everything we see and touch and are. The knowledge that we are made of star stuff trying to understand itself. Can beauty make you immortal? Perhaps not. But the quest to understand beauty, to understand why the universe is comprehensible at all, might be the closest thing to immortality we have. The discoveries made at CERN will outlast every scientist who contributed to them. They will remain true long after the buildings have crumbled and the machines have rusted. The dance continues. Shiva still dances in the courtyard. Particles still dance in the tunnels. The cosmic dance of creation and destruction plays out on scales from the subatomic to the astronomical. And we, briefly conscious arrangements of quarks and electrons, get to watch and wonder and ask what it all means. That is the gift of CERN. Not just the technologies it has spawned, not just the discoveries it has made, but the reminder that we can ask these questions at all, that we can build machines to probe the smallest structures in the earliest moments, that we can work together across borders and languages and histories to push the boundaries of what is known. If you enjoy these deep investigations into the mysteries of science and the stories behind them, please like this video and subscribe to the channel. Your support makes these detailed explorations possible. Tell me in the comments, what scientific mystery should we investigate next? The search for dark matter, the origins of life, the future of artificial intelligence. The universe is full of questions waiting to be asked. These stories are not just about machines and particles. They are about us, about what we value, about what we are willing to invest in, about the kind of civilization we want to be. CERN started as a dream in the rubble of a shattered continent. It grew into the largest scientific collaboration in history. It discovered the particle that gives mass to everything. It invented the technology that connects billions of people, and it is still going, still searching, still asking what else is out there waiting to be found. The truth about CERN is not that it is opening portals to hell, or shifting timelines, or summoning demons. The truth is simpler and stranger. A group of humans built a machine to understand what we are made of, and every time they turn it on, they learn a little more about the universe that made us. What could be more remarkable than that?